Ok, muy buenas tardes, gracias por venir a esta charla. Y dado que tenemos un invitado extranjero, la presentación va a ser en inglés. Okay? So, in this opportunity we have the presence of Professor Felipe Fanchini. He's an associate professor at the Sao Paulo State University. He's an expert in different fields of quantum mechanics, especially in quantum information, quantum computation. And in the past year, now he's interested in application of quantum machine learning to real problems. So, Felipe, you have unlimited time to introduce the main concept of quantum machine learning. So,
thank you very much. Thank you very much for everybody here today. It's an enormous pleasure to stay here to visit Chile. I visited Chile maybe 25 years ago, so it's my second time in Chile. And honestly, I'm very happy to stay here today to talk a little bit about my work, what I have been studying the last years. So I began my studies in physics in 2002 as a master. Then I developed a PhD studying open quantum systems. Then postdoc with Professor Marcos César de Oliveira and as a tutor Professor Amir Caldeira, studying quantum correlations, quantum discord, and since 2016, 2017, I just began to study machine learning, classical machine learning, to study physical problems. At that time, we were trying to find some tools to help instrumentalists using machine learning. And since 2019, I began to study quantum machine learning, and this is my talk today. So, if you would like to stop at any time, please, you can interrupt me. It will be a pleasure to explain, to give my feedback about quantum machine learning, quantum computation, and other aspects that I can have. Okay, so here is a brief summary about my talk. I will give you an introduction about noise intermediate scale quantum era. That's an era that contains few qubits subject to noise. So when we are talking about quantum machine learning and in quantum optimization, I think that the main focus on this area is because we are nowadays with computers that has few qubits and noisy qubits. So this is why I believe that the first implementation of real applications of quantum computers will be machine learning and mainly optimization. So I will talk about disk devices and quantum errors to explain why it's important to have new algorithms different from that classical ones like Shor, Grover. Then I will talk a bit about classical machine learning. I don't believe that everybody knows about classical machine learning, so I will give some feedback. And then I will present the main ideas concerning quantum machine learning. I will present a zoo of algorithms where people use quantum machine learning, and I will intend to explain the importance of these algorithms nowadays. And to finalize, I will talk a little bit about work that we did together with a group of NTT Data. It's a company of big data, multinational company. And our application will be to calibrate question-answer systems using quantum neural networks. Okay, so let's begin. Just to give an introduction about quantum computing, here is a timeline that I believe that is the most common one. So the idea of quantum computing began in the 1970, 1980. The Russian guys was the first, in my point of view, that pay attention to the power of the quantum physics to develop quantum computation. Then we have Feynman, that is I believe that's the most important to spread this news about quantum computation and how it will be important to have a quantum machine to simulate quantum physics, because when you increase the size of a quantum system, you don't have enough memory, classical memory, to work with this amount of data. It's increased exponentially, so it becomes important to use the quantum law to study the quantum physics. But the idea at the beginning, nobody knew how to use this, so since I believe 1985, Deutsch presents the first algorithm, and Bernstein-Vajrami, I think that 1994 with the Peter Shor algorithm to determine the prime numbers of the root number. This is, I think, that after this period, things change when you are talking about quantum computation, because at that moment, people noticed that it was quite powerful, that we can solve problems that at least until today, we don't know how to solve in a classical computer. So Peter Shor is the first step, in my point of view, to change the root of the quantum computation. Then we have in 1995 the first implementations, Grover algorithm to search if you have an unstructured data set, then Grover presents an algorithm to make search in this data set. It's faster than no classical algorithms. Then you have the implementation of Grover 998, 2001. We have the first implementation of the short algorithm, so it's 20 years ago. In 2012, John Preskill presented the idea of quantum supremacy. That is the idea that you have algorithms implemented in a quantum computer that we cannot implement in a classical computer. We already suppressed these points, but just for toy models, we already implemented some codes that it's impossible nowadays to be implemented in a classical computer. But at this moment, this algorithm is just as curiosity. There's nothing that we can do in fact. And also in 2018, John Preskill again coined the term noise intermediate scale quantum era. That's related with processors that contain 50 qubits and 50 or more, 100 qubits, 200 qubits, and in a situation of having noise. So the idea, maybe 6 years ago, is it possible to use these computers that we have nowadays to implement some practical tasks? And in fact, we are looking for this nowadays, but at least people believe that we have a good chance to implement practical tasks using these kinds of processors with few qubits and noise qubits. So it gives a brief timeline of the quantum computation. So here's the age that we are nowadays, is the NISQ era. And when you're talking about quantum machine learning and quantum optimization algorithms, you should think in NISQ. Okay. So, about NISQ era, we are mainly talking about variational quantum algorithms. Variational quantum algorithms are some algorithms that you have some parameters that you can adjust, and we use classical computation to adjust these parameters. This is the idea. Here are some examples: variational quantum minus solvers, quantum approximation optimization algorithm, WAWA, variational quantum machine learning, but there's more than this. We have a quantum annealing, Gaussian Boson sampling, analog quantum simulation, digital analog quantum simulation. Today I will talk a little bit about variational quantum machine learning. I will try to explain you what's the idea behind this and why people believe that is probably, together with the optimization algorithms, it will be the first applications of a quantum computer. At least is what the community that works with quantum computation believes nowadays. Okay, if you would like to find a review, you have a recent review from 2022, a review of modern physics. So here's just who has the interest to have a look what's new, what's going on when you're talking about noise intermediate scale. Okay, so I believe that the first step here is to say why should we think, why should we work with these devices. I will try to present for you a simple example, since we can together understand what's the problem nowadays with the quantum computer. Why we don't have a functional quantum computer nowadays? What's the problem? It's not just noise. There's other problems that we need to solve. Okay, so to understand this point, I propose you a quite simple experiment. The idea is that I begin with a state of 0 and then apply what we call as a bit flip. Bit flip just rotates your state from 0 to 1, and of course if you apply 2 times it returns to 0, and the idea is to do this d times. So here's a plot as a function of d, and here I'll calculate the expectation value of sigma zeta. So if it's 0, it is 1. If it is 1, the state is 1. We have the expectation value as -1. So if you have an ideal quantum computer, what you have is that it will reach 1, -1. If you have 2-bit flips, 3-bit flips returns to 1, 4 -1, so it will return between 1, -1, 1, -1, 1, -1. This is an ideal quantum computer. If you have a functional quantum computer, it works exactly as you have. Okay, but the reality is not so beautiful like this plot. The problem is that we have some problems when we are talking about quantum computing. One of them is called coherent errors. Coherent errors is a control error, because the point is that when we intend to implement a rotation, a simple rotation, sometimes we have some delay in the control. It's quite common. And of course, that even that it's so small, if you implement a random case, in the end you reach something like this, because it's a cumulative. So every step, every round, it gives 1 epsilon, and the second one 2 epsilon, 3 epsilon. So in the end, what should be something like this, it's kind of like this. And this is, there is no noisy, there is no environment, there is just a problem in control. And it's real, it appears in a quantum computer, and of course that we need to try to make this as 0 as possible. So we intend to have a full control and a perfect control, but we know that it's quite difficult, even nowadays. So it's one kind of problem. It's called coherent error, and it is a control error. This is one kind of error that we have. The other is the environment. For example, if I introduce plus to this coherent error and bit flip error, I mean the environment, given phonons, photons, a lot of possible perturbation. Sometimes your qubit that was 0 becomes 1, so it's a kind of external perturbation. It's an incoherent error, and the result, if you have this with this, is something like this. So what we see that things will become critical if you have incoherent error plus coherent error. And this is just a part of the problems. We have more problems when we are talking about real quantum computers. One important problem is the readout assigned error. A problem that I have when I intend to read the data. Just to read. Suppose that I have everything work perfectly, no coherent error, no environment, but in the end of the computation, I have mistakes. I prepare the state on 0, but given some problems, I just measured 1. It's a readout assigned error. This is it's maybe cannot read here, but I explain you. This is a IBM quantum computer. Here's the value. Is the best qubit that they have has about 1%, a bit less than 1% of readout error. It means that each 100 times or 200 times one of the measurements, it was supposed to be 0, but we read 1. Okay, then you can say, okay, it's not a big problem. In fact, it is, because if you introduce a set with 200 qubits, it also is accumulative, and the purity of the system, just with readout errors, just reach almost 0. This is exactly this value that we have nowadays quantum computer. So just prepare 100 qubits, all of them on 0, but I need to calculate the probability to have a lot of shots, a lot of implementations to take the probabilities. But every time one qubit was 0 becomes 1, the other qubit was 0 becomes 1. In the end, when you take your final state, the purity of the state, that's a measure of how good is your distribution, is almost 0, just for 200 qubits. So it's also a big problem. Even that I don't have coherent errors, even that I don't have incoherent errors, just the readout error just make the information vanish if I have just 200 qubits. Here there is no algorithm, there is no protocol. I just prepare and measure, and this is the result, the final result. So the point is that you have a long way to take yet, and this is why people are thinking that it should be important to see if there is some algorithms that could work with this machine, with this quantum processor, with error, coherent error, incoherent error, readout error. Is it possible to do something useful nowadays? We are trying to see. There are some new algorithms, but to be honest, at least to the best of my knowledge, until nowadays we don't have anything that is in fact practical, that gives some new results or better results when compared with classical. But even that, I will explain you why it's important to begin to study and to understand this kind of algorithms, mainly quantum machine. Okay, just to present an example, in this study presented by the group of Microsoft in the last year, 1 year ago, they study how many qubits they need to implement some practical protocols. And what they show is that if you intend to implement factoring, quantum chemistry, quantum dynamics, you need, this is millions. So we need 1 million, maybe 10 million qubits. And you are talking nowadays about 200. So if you wait to implement this, probably it will take a long time. So these classical algorithms we will need like 10 million. Quite recently there is a new error protocols, protocols, protection of errors, and this number is divided per 10. But even that, we are talking about 1 million qubits, around 1,000 qubits, or 10,000 qubits. So it's a bit far nowadays to try to implement this kind of algorithms. This is why we are trying to find some important results using these new kinds of algorithms, like machine learning and quantum optimization. So it's very difficult to work with quantum information. Okay, so before to talk about quantum machine learning, I will explain the main idea behind the machine learning. What is a machine learning? Classical machine learning. What's the point? When we are talking about a machine to learn, what it means? Okay, the idea here, of course, that is much more than this, just an example, but the idea is the following. I have a set of data, when I have some features, and I have one target. These features you can think, for example, if you are trying to study price of houses, you have the number of the rooms, the area of your house, where it is located. So you have a set of features, and given this set of features, I can return a price. And then you take a data set with many houses, with prices, area, number of rooms, if there is a swimming pool, a lot of features concerning your house, and you have prices of a lot of these houses. The idea is to try to determine an algorithm that, since I take new features, then I can estimate the price of the house. This is one application of classical machine learning. Of course, it can be used for many purposes. When I'm talking about physics in my studies, for example, I have been studying the degree of non-Markovianity of a process. So I take many expectation values, measure in many times, and then with this amount of data, I try to determine the degree of non-Markovianity of a quantum process. And it can be used for a lot of applications. So the point is that I take these features, I present to my code for my computer, and what I intend to do is to determine these targets. If I'm talking about supervised machine learning, that's the point here. As I said, you have this data, a lot of data, and then I try, given this set of features, to determine new targets to see if it's related to this. This is the main idea. So, when you're talking about machine learning, we have a data, a model, and a cost function. The cost function is the difference between the real data and the data that you suppose that is the right answer. So to training a quantum machine learning, in general, we divide this data set in two parts, using this part, the training data set, to calibrate, to adjust a set of features, a set of parameters, and also using this target, I calibrate to try to make this cost function, this difference of what I learned and the real data, as possible. So I'm going to adjust these parameters since I can try to determine these targets, and also I minimize my errors. Then I take this test data set that I do not use, I reserve it in the beginning of the algorithm, and then I compare to see if it's working. Because I don't use this red part, but I use this blue to calibrate parameters. Then I use the parameters that I calibrate to try to determine the target of this red data set, and then I compare. Okay, it's good, oh, not so good, good. So I take the difference and then I calculate my error, the percentage of errors that I have during my learning. This is the idea, basic idea concerning classical machine. Okay, so just to illustrate, a training data, a model. This model can be, depends of your task, so it can be quite, there's a lot of different models. Then I have a cost function that I will determine if the results that I have and what I predict is near enough. With this difference of this cost function, I adjust my parameters. Theta is my set of parameters that I try to adjust. It's like a big matrix that I try to take the best parameters as possible, compute this gradient to adjust these parameters, then I update, try again, calculate the cost function, try to adjust your parameters, update, and then you do this until you find the best set of parameters as possible. This is the main idea. Okay, this is a classical machine learning. Once you train your model, then you test, you take that part of your data set that you reserve, and then you check to see if your set of parameters that you determine is okay with the prediction. So I compare the prediction with the real data. This is the real data, this is the prediction. I compare and then I calculate the error of my model. Of course, that it's in general it's not exact, but you can minimize the amount of errors that I have when I calculate this cost function. Okay, this is what we call classical machine learning, and the point is, what is quantum machine learning? What about quantum machine learning? What's the difference? Okay, first, before to talk about quantum machine learning, it's important to separate in 4 different points. So the classical machine learning is this CC. You have a classical data processed in a classical computer. But you can have quantum data processed in a classical computer. This is of course quite difficult because in general, if you are treating small quantum states, we have a lot of data and it's quite difficult to process in a classical computer. But you can have also quantum data processed in a quantum computer. And what we will talk here today is classical data processed in a quantum computer. So I have some data that I have in my classical computer, and I want to try to develop an algorithm to learn, and this algorithm runs in a quantum processor. At the end, I measure, take probability distribution, or in other words, I revert this as classical data again, and then I adjust my parameters and I continue my computation. So here I will talk about this aspect. Good. So classical data processed in a quantum computer. How we will do it? What's the strategy to treat classical data using a quantum computer? So here's our model, classical model, when we are talking about machine learning. And what we will do here is to change exactly this part, just this part. So we have a classical data that in some way I convert in a quantum state in a quantum data, processed in a quantum computer, measured to make it classical again, then the routine continues. I calculate the cost function, compute gradients, update data, update my parameters, then I just take my data, put in a classical quantum state, process using quantum state measure, and this is the main idea. People think that's important because when you are talking about the Hilbert space, that is the space where the quantum state lives, we have a huge space. It's so big. So the point is it possible to treat this classical data in a quantum environment, in a quantum state, as a quantum state, to see if we can take some advantage? People believe that it's possible, but until today, there is just, at least to my best of my knowledge, there is just one case that it was proven that you have advantage. Yes, but the point that these algorithms use as a basis the short algorithm. So a step of this case is to use the short algorithm. So we are not talking about the Nice era. We are talking about an era where you have fault-tolerant quantum computing. But there is at least one case proved mathematically that it's quite different from the classical one. It's impossible to implement this in a classical computer. But it's not for quantum computers working in this way. So the point is to change the model. We change the model for what we call as a variational circuit. This is the idea. So here is the main difference when we are talking about quantum machine learning and classical machine learning. The model is quantum. Okay, so things are a bit different. First, we need to encode our classical data in a quantum state. Then I apply a parameterized model. It's a model that has some parameters to adjust. I will explain in a few minutes. And then at the end, I'm measuring the qubits to get the labels. This is how it works. Note that this classical data is encoded in a quantum state, and at the end, I return it as a classical data again after my meeting.
Sorry, when you say convert again to classical data,
Yes.
you mean parameter estimation
from the measurements? I measure of them and take a probability distribution. And I take this probability distribution as a data that I will try to use to determine my, for example, my label. This is the idea. This was clear?
Okay.
Yeah. So, for example, I have the probability to have 0 and the probability to have 1. And then, okay, if the probability to have 0 is bigger than a half, then it's blue. If it's less than a half, then it's red. Then it's a classification between red and blue, for example. Okay? So, there is many different strategies to encode classical data in a quantum state. You have basis encoding, amplitude encoding, angle encoding. So there's different ways to encode a classical data in a quantum data. Just an example here, I will just show you what's the idea about angle encoding. So here I have, for example, 4 features that determine, for example, if we have a Markovian dynamics or a non-Markovian dynamics. These 4 parameters I codify in the rotation of the state. So if it's x1 is 0, the state is 0, but if it's x1 is, for example, 0.3, I apply a rotation calibrated by 0.3. If it's x2 is 0.5, then I rotate this one by 0.5. If this is at 0.7, I rotate this. So it's calibrated by the feature. The rotation is calibrated by your 4 features, for example. After you do this, you have then your data encoded in a quant state. This state, of course, not more all zeros. This is 0. This is a superposition, another superposition. Depends of x1, x2, x3, and x4. After this, you just introduce a parameterized model. What is a parameterized model? I will explain you up here right now, but it's like a set of gates that depends of some parameters, and the way that you choose this parameterized model, you can try. There is many ways to do this. For example, use a set of different parameterized circuits. This is a simple one, but you can introduce control nodes, and so big, and you can also repeat. Take this, then put again, put again, put again. You increase the size of your circuit. The idea is that each one of these gates, each one of these operations, this is a unitary operation, but just right in terms of circuits, but it's a set of unitary operations. Think about a general unitary operation that depends of a hundred of parameters, and then I try to adjust these parameters to see if in the end, after I measured all qubits, I can classify a data better than a classical, for example, algorithm. This is the idea. So, and the idea of these circuits, this parameterized model, is to try in some sense to spread your information in the Hilbert space. So, depends how you parameterize your model, you can make your data to populate all this big space of the Hilbert space, and the idea is to try to see if I can take some advantage using this parameterized model. So here's an example of a parameterized model, a control unitary evolution that depends on the parameter, another one, then local operations of them with some parameters that I can to adjust to see if I can obtain better predictions than the classical predictions. As in the classical model, first I use some data set that to train, so I know the answer and try to adjust to commit as less mistakes as possible. And then I test with a part of the data set that you use it as a test data set. So in the end, I measured everything, and after your measurement, then you convert your data for classical. So it's a probability to be 0, probability to be 0, probability to be 0. Then I can sum, for example, the probability of the 2 qubits, the probability of the last 2 qubits. You can choose whenever you want to try to find a way to better predict your targets. This is the idea. So here's just to summarize. Training model, this is my model now. After a measurement, I take, compare, calculate the cost function, actualize theta, update, and then return to my quantum. Just this part is quantum. This is classical, 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 and the model, just the model, is that. This is one kind of quantum machine learning. Yes, there's other different ways, but I'm focusing on this one. Okay, there's one important aspect that I would like to emphasize, is that because I already present this in other places, and it's important to notice that quantum machine learning is important in my point of view, and there's few people talking about this, even if your algorithm is worse than classical algorithm. And you get, okay, why? Because there is no way to treat, for example, informations that you have codified in a quantum state. But you can say, okay, but if I need to take your classical data and to include in a quantum state. So it's possible to treat this as a classical machine learning algorithm, with a classical machine learning algorithm. But in some cases, now talking about quantum data, it's impossible to convert this as classical data. So, for example, suppose that you have 100 qubits to implement a simulation. In the end, you have a state that has 2 to 100 parameters. I cannot convert all this information as a classical information to treat using classical machine learning. So the unique way to treat this total information is using a quantum machine learning algorithm, because it's impossible to convert this information in a classical data set. So even that your algorithm is worse than the classical one, for example, for some tasks, even that, it's important to understand and to develop these algorithms, because in a recent, maybe 10 years, it will be the unique way to treat quantum data. There's no way to treat in general. Of course that you can take part of your information and convert to classical information. But if you intend to take all the information to work with it, you will need to work in a quantum state. And then the unique way to treat it is using a quantum machine learning algorithm, because it's impossible to convert this data in classical. So this is one aspect that I need to emphasize. But it's not the case here. Here I'm talking classical data codified in a quantum model. Okay, so since I give this brief introduction, now I will try to give some examples what is nowadays, what people are developing when concerning quantum machine learning. There are some algorithms, all of them are based in classical algorithms, but then people try to use the trick and the advantage of the quantum to try to develop more efficient or even faster algorithms. So the first one is the usual SVM, for example, with support vector machine. Then you use classical data codified in a quantum state to try to determine labels, for example. This is for classification. You want to classify between blue and red, for example. This is the first simple one. The idea here is that this is called as a feature map. Feature map is like a transformation in your data. For example, here you have green and red, and it's impossible to separate it using a linear structure. So you implement some kind of codification to separate this. You extend your space, and then you define with this algorithm some hyperplane to separate between red and green. This is the idea when you are talking about support vector machines, classical support vector machines. Here we are doing the same, but in a Hilbert space. You just put your data in the Hilbert space, it's spread in this space, then you apply a feature map to see if you can separate this around this new, inside this new quantum space, and then you determine hyperplane to separate, and then you also give new data. If it's over this plane, it's red, it's above, it's green. Is it possible also to use the idea of quantum kernel estimators? I'll not take so much time to talk about this, but this is a different way to treat support vector machines. There's a primal and dual way. This is equivalent to dual way, and in fact it's more general than this one. This one is inside it. So this is a different way, but it's the same idea, but it's richer than this one. Don't worry. just to accept. Okay, also one point that's important, because if you are talking about deep learning, you need to introduce some non-linearities in your data. Contrary, you can just take all your layers and just change for one unique layer, because if it's linear, so it's important to introduce non-linearity. And there is some studies showing how to introduce a non-linearity in a quantum module, because quantum mechanics is linear, but measurements are non-linear, so you use some measurements to introduce non-linearity in a quantum protocol. This is the idea, and it is important, as I said, because when you are talking about deep learning, it's important to have this many layers concerning our algorithm. This is another method to introduce non-linearity. So you see that you have a function that is a non-linear shape. It's just to mention that it's possible to introduce non-linearity in our models when you consider measurements. This is the main idea. There's many different ways to introduce non-linearity. We have neural networks, quantum neural networks. So the idea here is to take your features to try to determine some parameters to classify between red and blue. Here we have a repetition of your data, you include your data, a set of parameters, you codify your data again, you have a set of parameters, and again. This is important because we cannot clone quantum information. So if I want to connect this with this learning, I need to codify my data, and if I intend to use this with B, I need to codify again, this with B, so I repeat. It's called repetition of your data. So it's equivalent to our quantum neural network. Each one of these is a neuron. Here, each neuron is a set of gates. I can introduce more layers, and I introduce more layers, introduce more qubits. So the introduction of multiple qubits may improve its performance as more hidden layers improve the classification task of an artificial neural network. So it's equivalent to a deep learning. There is a quite analog algorithm to do this. More. See, here's the idea. So layers means more qubits, and neurons means more layer, more the depth of your algorithm. You repeat the set of the gates to introduce more and more neurons in my network. Also, we can codify more than one class. For example, if I intend to, in one qubit, to determine 4 classes or 6 classes, I just divide the sphere, that is the block sphere, in different parts. So here's class 1, class 2, class 3, and class 4. Here I divide in 6 parts, so class 1, 2, 3, 4, 5, 6. So it's possible to determine or define multiple classes in one unique qubit. This is the idea behind this. Also, it's possible to prove universality. Machine learning, you can plot, you can determine any function using machine learning, and the same was proposed using quantum machine learning. The idea is to use a Fourier series, and then you can also use quantum models to determine any function that you desire. So it's possible to describe a function using a quantum model as well. You see that this paper is quite recent, these ideas are quite new. We have also, we call it quantum convolution neural networks. It's called CNN in the past one. CNN is used, for example, to determine images, to classify images. You can do the same using a quantum algorithm. You introduce measurements, and in the end, you measure and then you see, okay, it's a cat or it's a dog. So each pixel of this image is codified in a quantum circuit, and then you will go adjusting more and more layers, more and more parameters, and in the end, a unique measurement can say if it's a cat or a dog, for example. If the probability to be 0 is higher than to be 1, then we define as cat, contrary, we define as dog. It's possible to do this. There's no advantage when compared with the classical, but you can do this in a quantum algorithm as well. Also, you have quantum filters. The idea is to take an image and try to make it smaller and smaller, and in the end have just one pixel, but this pixel brings the information of all your image, and you do this just taking, for example, 3 by 3, and then you convert this in a unique pixel, for example. And then you reduce your image to the end, determine if it's a horse or a dog or a cat. This is what we call CNN. We have the analogy as a quantum zone. So the idea is like this: take each picture, include it in an algorithm, a parameters algorithm, measurements, then you have many features, then you can develop the same idea. This is quite interesting. It's called GAN. GAN is what we as well know as deep fake. So it's possible also to introduce deep fake in a quantum computer, and this is, in my point of view, quite interesting. Here is the first GAN, but it's not Tom Cruise. This is, what's the name of this guy? First GAN is Tom Hanks, and I will remember at the end. This is John Travolta. John Travolta, yes. So John Travolta was invited to be the first GAN, but he said, "Oh no, it's not a good movie. I not do this." Then this is a deep fake. Okay, what is going on here? This is important because I think that it has applications in physics and in many other areas. The idea when you're talking about GAN, that's deepfake, is that the following. I have a real data and I have a noise, a fake data. And then I go to adjust this data since I have a discriminator that try to say if it's fake or not. So you adjust your noise, your fake data, since that your discriminator do not recognize what is real and what's fake. This is how deepfake works. You just go to adjust your data, follow some rules, and in the end, the discriminator convert. You cannot just say, okay, it's real or not. This is important because you can take, for example, physical data, and then you intend to try to describe this physical data in a quantum circuit. So you begin with a quantum circuit general, all disorganized, and then you begin to adjust your circuit since that in the end your distribution of probability is equal to your real data. So in the end, your circuit, a quantum circuit, you describe your real data, the data that comes from astrophysics, that come from high energy. You can find a model, a quantum model, to describe some physical process. This is the idea. So it's quite important because it's important for simulation. You can simulate some astrophysics results using a quantum circuit, using quantum gates. This is, in my view, quite important as well. Okay, and to finalize, okay, here's the idea. Noisy, data qubits, introduce, generate output, and then try to see if your algorithm do not recognize what's real and what's fake. So, I'm almost there. To finalize my talk, I will just talk quite briefly about my work. And this is what we use to learn about quantum machine learning. So it was submitted 1 year ago. We are nowadays fighting with the reviewers. But it was important for our group because it was our first time. So I just explain quite briefly what is going on. The idea here is to use large language models. So the point is that nowadays it's quite famous, GPT. We use BERT. BERT is a previous language model by Google. And these models, in general, they gave some notes. There's a lot of parameters here, as you cannot see, but it's billions of parameters to train these models. There's some, how could I say, faster, smaller, lighter models. The Stilbert, Roberta is a more robust method. It's a new second generation of the BERT. You could say this. This was developed by Facebook. This is by Hugging Face community. This is the faster because this is quite difficult to train, to implement, and to run because it demands a lot of processing. And this one is easier. So this is the idea. And the calibration here means that sometimes these algorithms give some answer with a high score, but in fact it's not the right answer. So you need to calibrate the percentage, the score that they give for an answer. It's important because, for example, if we're talking about autonomous car, it would be dangerous if your machine say go and you should do stop. So to have a precise answer with a high score and well calibrated is quite important. And here we use a quantum algorithm just to calibrate. So we take our language model, we use it classically, and it gives me a score of its answer. For example, this answer has 70% to be right. And then I just calibrate this percentage trying to use a quantum model. This is like an example of uncalibrated model. They said that you have 40% to be right, but in fact it's 20. This 6% is right, but in fact it's 35. So I try to adjust this curve since that it could be in the middle, since we say 0.4 and in fact it's 0.4. It's 0.6 and in fact it's 0.6. This is what we call as calibration question answer systems. Okay? This is what we do. So of course there is not this amount of data. When you try to calibrate, we use just 5 features. I will just show you in a minute. So here's, for example, some uncalibrated data. You see, they said that it is 0%, but it's in fact 45. Here he said it's 100% to be right, but in fact it's 0.5. And here we use 2 different data sets. The SQUAD is an open data set, and this is an internal entity data. As features, we use 5 of them, so it's beginning of the answer span score, because each word has a score. Each word in your answer has a score. So I use the score of the first word, the score of the last word, the number of words in the question, number of words in answer, and the probability there is no answer. These are the features that we use to try to calibrate our answer. It's done also classically, but we did the same using a quantum algorithm. So here's our model. We use algorithm to codify the data, parameter parameterized algorithm, and we develop the measures in the end. So here is the calibrated data, and here is the uncalibrated data. You see that the error of a calibrated estimation is 0.7, 0.15, and here it was like 0.54, I think so. So it calibrates. This is using a quantum algorithm. It's the same here. The estimation calibration error, it's 0.05, 0.05, and here it was too high, 0.53. This is what we used to learn quantum machine learning in the past. It's a simple toy model, but it works as the classical algorithm. Okay, so to conclude, what we would like to say is that this area will certainly, in my point of view, the next step in quantum computing. Creating robust qubits will be crucial for the development of functional quantum algorithms. Here we provide a very concise overview of applications for variational quantum circuits, and in the end we show how variational quantum machine learning can be used to calibrate question and answer systems. That's all. This is my group that have been working nowadays. This is a class that have nowadays present for companies. Companies in Brazil are looking for quantum computation, quantum simulation, quantum optimization, quantum machine learning, and we are preparing some courses for these companies in Brazil, just to mention, and that's all. Thank you very much.
Okay, we have time for some questions.
1 hour precisely.
Wow. Tenemos tiempo para preguntas, así que puede levantar la mano. Diego?
Sí. Good presentation. Thank you.
Thank you.
In your experience, what methods have more accuracy, quantum kernels or variational quantum sequence?
Quantum kernels will sure, because as I show you, when you are using variational quantum circuits, they are inside the quantum kernel. So the quantum kernel is an extension to the variational quantum circuits. One is contained in the other.
But I see a problem of variational quantum circuits called barrel plateau. You see before, no?
I don't know, depends.
Barrel plateau.
Barrel plateau, I know. Yes, I know.
Yeah,
Yes.
I've never seen before of quantum kernels methods have that problem, because I think it's another method. Quantum kernels don't have barrel plateau problems.
Honestly, I don't know exactly what's the... I understand the problem of barring plateau. When you increase the number of qubits, your surface just diminishes, like becomes a flat.
Yeah.
Yes, I know. But
function, no?
I don't know exactly what's the problem when you are considering kernel or variational quantum circuits. I'm not an expert in this area. I don't know. So I don't know.
Yeah, okay. Well, thank you.
Okay.
Any question?
Yes, typically these models, the quantum models, works with how many qubits? I think that you said that, but
In fact, you can introduce this in 127 qubits. That's the IBM quantum computer. But the point is that it's too noisy. Main point is that the number of gates that you need to implement in a circuit. Because, for example, if you implement a single control node, that's one gate, it takes about in the order of nanoseconds to implement this. Okay? But the time to occurrence in a quantum computer is the order of a microsecond. So, more than important the number of qubits is how many gates you need to implement. Because if you need to implement 1000 gates, then the total time will be bigger than the time of the recurrence. So I think that the most important than the number of qubits is, and there's other points that's important to mention, because these qubits has a fixed structure in our computer. For example, this structure. And in these algorithms, in general, we need a connection between this and this, between these and these, so they are far. And then you need to implement swap gates to make this interaction between this qubit and this qubit. And it demands more gates, so it's quite difficult to implement this in a root structure. So nowadays we are working with simple modules, but there are some companies that are using, for example, classical simulation, using GPUs, for example, to have 50 qubits. So 50 qubits is a space of 2 around it, to 50.
And typically, which kind of qubits are physically the most promising qubits, the most robust?
This one is classical. They are simulating this in a classical computer. Yes, but they're simulating like a space, a matrix of this size, 2 to 50. They're using thousands of GPUs, thousands of memory, to try to see if they can develop something using 50 qubits. And then it's an ideal situation because there's no error. There is a simulation in a classical computer. But this is one area. And of course, that if you intend to increase this to 100, then forget about it. There's no way to do this in a classical computer. Then you need to do a quantum computer. But nowadays, given this structure, is quite difficult. Even that we have these computers with 127, as I said, the gates takes long time compared with 51 and 52, the time of recurrence, time of dissipation. So you cannot have, it's impossible to implement 1,000 gates, for example. Was it clear?
Yes, thank you.
Yeah?
Yeah, in which case is better option use quantum data or classical data?
We don't know yet. We are trying to determine exactly if there is some advantage using quantum data compared to classical data. The unique case that I know, they use short algorithm as a step of the algorithm. The point is that, what could I say as a give some advantage? The transformation that they develop in the data cannot be implemented in a classical computer. But the first step is to implement this transformation, but the second step is to see if it's usable. So we don't know yet. We are just looking for some applications nowadays.
A very stupid question. What is quantum data?
Quantum data? Quantum data is a quantum state. Suppose that you are using, for example, you develop a quantum simulation. You try to simulate a molecule. So you can try to describe the wave function of a molecule in a quantum computer. In the end, you have a state. This is a quantum data. This is a data that it's impossible to convert totally. Of course, that you are talking about 100 qubits in a classical data. This number 2 to 100 is bigger than the number of atoms in the universe.
But that only exists in a quantum system.
No, there's 2 points. Here I'm talking classical data that is processed in a quantum computer. So I take a data set, classical data set, then I codify it in a quantum state, given some strategies. There's many different strategies. I manipulate this data that's now codified in a quantum state, and in the end I imagine to take back as a classical data. This is what I call as CQ. Classical converted to quantum, processed in a quantum, and then in the end I measure to obtain some feedback, classical feedback. But in my point, what's important in classical machine learning, in quantum machine learning, is key. Quantum data processed in a quantum processor. And in this case, I have a quantum state and I intend to try to take feedback. For example, this molecule has a hydrogen, has not hydrogen, this molecule has dissociation or association. Is it possible to connect with another molecule? If I intend to work with this amount of data in a classical way, it's impossible because I cannot to describe all the parameters that describe this wave function, because the amount of parameters is this one. So it's impossible, at least in theory, to implement in the end not a measurement, but a new algorithm, a quantum machine learning algorithm, to obtain an answer, for example, if this can be associated or dissociated. It was okay? Not so much. We can talk here some more. We can talk some more.
So in other words, you take a quantum bit, a qubit, with many levels.
Yes, it is equivalent to a quantum bit.
Somehow you include this classical information in the probabilities or in the...
Okay, but you don't have the total information that you have in a qubit, yes? Because a qubit has...
So how do you generate this quantum state? That's my question.
This quantum state?
Yes.
Okay, there is another algorithm that is used to simulate, for example, a hydrogen atom. Is it possible to, in the end, you simulate dynamics of a quantum state, for example, or describe potential, or describe other. And in the end, you have a wave function that, for example, describe the ground state of a molecule, for example.
No, I understand. But how do you, what's the process to get the classical information into quantum?
To convert classical to quantum, do you mean?
No, to feed this quantum.
I don't know if you understand your question.
You say that this is a process that you go from a classical information, right?
Yes, classical information.
And you feed this classical information into the quantum system.
And exactly, I feed this in a
How do
quantum
you
system.
do that?
I can do this in a different way. For example, suppose that I have this set of quantum classical data, okay?
Okay.
I can, for example, apply in this case a rotation on x calibrated by x1. I can, in the second qubit, a rotation connect with x2, and this x3, but I can do different also. I can also introduce here a product between x1 and x2, and this control, for example, your rotation here.
Yeah.
So, in some, but you can also, for example, implement here a control knot that depends of this parameter x1. So you can create different strategies to codify a set of data in a quantum state. In the end, you have a state that will depend of these parameters that it gives your data sets. It's a state.
How do you relate this with the hydrogen atom, for instance?
You do this applying electromagnetic fields for a certain amplitude for a certain time. Then you depends of the time and the amplitude, it's codify x1. This codify x2. This Rx is something like this. Rx x1 is E minus E x1, something like this. Yes. This is the sigma x. Yes, this is sigma x. But this sigma x has a parameter x1 that control the amount, how they rotate this state. So in the end, you have some state that is 0.8 is 0 plus 0.21. This is the first qubit. The second, a different distribution of probability. The third. So I codify x1 in this. This is one strategy, okay? But there's different one. You can rotate also in z, for example. You plug in plus, minus, then you rotate in the z-axis. Or even you can codify for example, in this state x1, in this element of the basis x2, in this element of the state x3, then you create a superposition where this is the first data, the first feature, the other is the second feature, the third feature, then you can put here, for example, 8 different features in a unique state. This is what it's good. But there's different ways. We are just trying, it's like heuristic, try and test, try and test.
Yeah.
May I ask another question? Thank you, Felipe. Can you explain very shortly again the quantum filter? Because is that
Quantum feature.
no, the previous one, the quantum filter? No.
Quantum filter.
Yes, the quantum.
See in filter. This one.
Yes,
Yeah,
because.
okay. I will try to explain you in using.
Is this problem related to the idea of compressing information? To the problem of data compression?
Yes, in some way. This is a classical strategy but it cannot be reverted, okay? This is the main point. Because you lose information in the process. But this is used in classical CNN. Suppose that I have, for example, a picture with 9 pixels, okay? And then sometimes, of course, that you can use 9 pictures, but you can also use more than this kind of information. So, for example, I take a matrix that's a filter. What this matrix does? Take this, multiply here, and take, for example, the determinants. So it returns 4, just 1. Then you take this same filter and put here, and then it gives you another number. Take here, apply this filter, take a new number, apply it here, and then you take a new number. And then you can use this information and this information as feature to learn something about your. It's important because it can, for example, recognize noise, because you can noise and nose. You can, for example, prepare a filter that when it reaches a nose, it gives a high number. So he knows that it's a nose because he is prepared to determine a nose or a eye. So when you take here nose, not eye, not eye, not eye, then there's some. When it fits with an eye, it's high probability, well, high number. And then okay, here's an eye, here's a ear, here's a mouth, because it's prepared to detect parts of the body, for example. Do you understand? Because if it not recognize an eye, it gives low score. But when it fits with eye, it gives high score. Of course, that there's some variations, but it can determine similarities in your face, in your figure. Is this okay? It's clear?
Yes.
Any questions? So thank you to Felipe.
Thank you very much for your time, your patience, and thank you again.